class. Good afternoon. Welcome to the today's class. Today we are going to look at the delays and its modeling in Verilog HDL. In the last class, we have started off discussing about the delay. Let us recapitulate what do you mean by the delay. How do you model these delay values in Verilog HDL? Okay, and some examples we are going to look at that one. Okay. So anyway, first let us define what do you mean by the delay. Okay, so in order to define a delay, first we should know a system. Okay, whatever the system it is. Generally, we talk about the digital systems, right? If you take any digital system, so it cannot give you the instant digital output whenever we are giving an input signal. Okay, so because the system intentionally produces some kind of time elapsed to produce an output, whatever the time that takes to give an output by the system is called the delay of the system. For the delay of the system, the main reason is that the system consisting of the active elements called resistors. Those resistors will offer some kind of resistance and capacitances. So due to that resistance and capacitance, there is a possibility of time lapse in order to get the output. Okay, this time lapse we normally call it as delay. Fine. So that is how we can represent here also. We have taken a system something like this, a digital system. Okay, digital system. So we are applying the input is something like this. The system responsibility in this particular case is just transferring the information to the output side. Okay, so but the output cannot see instantaneous to that of one. But actually, what do you mean by this one? At 1 nanoseconds, it has to raise, but at 1 nanoseconds, it is not at all raising. Okay, so it takes some amount of the time. So this is the time. So this is the some amount of the time. This time it takes. So at the raising edge as well as the falling edge also can be seen. Okay, so therefore this is what the real type scenario. Okay, so therefore we can say that the system having some kind of delay. Okay, so the output will take some amount of the time to produce. Okay, now let us see what are the different type of delays that system can produce. Okay, so there is a possibility of three types of delays are there. One is rise delay, fall delay, and turn off delay. So how do we define the rise delay of a system? Okay, so normally we talk about the output signal representation. So it is the time taken by the output signal when it changes from any value to the logic one. Okay, we don't bother about the 90% to the 10% to the 90%. We don't consider those things in the digital point of view. We considered only the change, the time taken by the change. Okay, from any value to x, y, z, any value in the sense logic 0 or x or z, whatever the any value to logic 1. Okay, that is called rise delay. Fall delay means the time taken by the output signal when it changes from any value to logic 0. Any value in the sense logic 1 and x or z. So go to 0. So it takes some amount of the time. That time is called fall time. And digital point of view, that to digital circuit point of view, we have another one is called turn off delay. So it is the time taken by the output signal when it is changing from any value to high impedance state. Okay, it may be 0, it may be 1, it may be x. When it transferred to the high impedance state, it takes some amount of the time. That is called turn off delay. Okay, so that is how we can define the delay of the system. Okay, obviously every real system offers some kind of delay because because the element will allow this kind of delay actually. Okay, delayed version. Okay, next. So sometimes whenever we have designed the system in our laboratory, uh, that may not give you the exact delay values after the manufacturing. Okay, so there may be some kind of delay variations are there. Normally we will call it as tolerance. So if you consider x is a actual value plus or minus y, some amount of the time that will be added to that one. Okay, so that means for x can be the delay value can be a less than that you expected, or delay can be more than that you can expected, but typical value cannot be existed. Okay, then sometimes may not be possible. So in that perspective, the delay values can be a minimum value, delay values can be a maximum value, delay values can be a typical value. That is how the people will can say about the delays. Okay. Now let us apply the delay concept. That means we want to model a digital system. The system normally the real time it is offers some kind of delay. Now we need to model that delay also so that we can accurately uh, sample, or we can accurately model our circuit. Okay, so therefore let us how we can give these delay values or delay information to our logical circuit or a logical system. Okay, so for that perspective we are going to look at two type of delays that we can apply on nets as well as gates. Any wire at any line that is connected to two circuits, generally we treat it as a net. Okay, so if you are applying a net of some delay value, if you are applying, then we have to use something like this. So wire, for example, if we consider that the middle one is a wire. Okay, a is taking some, for example, two timing units, for example, then we have to give in this method wire ash to A, which means that A take a two timing units delay. So what type of delay it takes, whether rise delay, fall delay, turn up delay. So therefore, if you are giving only one delay, for example, then this value can be a minimum, this value can be a rise delay, this value will be the maximum, this value can be fall delay, this value can be a turn up delay. Okay, so then if you are observing this is the as to symbol, something like this. So how the simulator will produce an output signal? That means we are saying that a wire A is taking two timing units delay. Okay, then whenever you are simulating something, then it has to incorporate this delay and it has to produce an output signal so that the design is accurate design. Okay, therefore, so the simulator output is something like this. So initially we have a 0 here, and whenever we have a raise, it takes two timing units, right? So 1 plus 2 means 3. 3 takes a time. Okay, so therefore this is the entire thing. So this entire time is actually two timing units. So it takes two timing units, then it will rise. Okay, then it will rise. So again, it has to fall. Also, what is the duration of this one? The duration of this one is 2 nanoseconds. 1 to 3 means the duration of this one is 2 nanoseconds or two timing units. So it will be available up to the two timing units. Yes, this is the two timing units. Two timing units. After the two timing units, it will be going down. So after uh, two nanoseconds time delay means it is wrong. Okay, so three timing units, up to the three timing units it is started. Okay, at three timing units again it is going back to the one. That means it has to wait for another 2 nanoseconds. What is the 2 nanoseconds time for this one? So 3 plus 2 means 5. Yes, after 5 it will going down this one. Okay, so therefore it is waiting for 2 nanoseconds time, right? So again it is taking this is the time delay that is taking. Okay, then it will go back to 0 again. So therefore this is how we can see. Okay, so the turn-off delay is not at all possible to show. That's the reason why I am not doing this one, because for that wire, it cannot go to the that state. Again, you can see here, let us consider the two delays now. Okay, that means first one, second one. It says that the first one is a raise delay information, second one is a fall delay information. Okay, so therefore it is started here. It is started here. Okay, so then again it finds the change at one. Okay, so at one means we have to go to the one directly, but it's not do that one. Why? Because it offers some kind of delay. How much delay it is offering? So one nanoseconds of time, for example. So therefore this is what? 1 nanosecond time. So therefore up to this 1 plus 2 means 3. At the 3 o'clock, at 3 nanoseconds only, the signal will be available. So therefore 2 nanoseconds delay is observed here. Okay, so again we can find at the 3 nanoseconds we find there is a low value. So that means it has to wait to another 1 nanoseconds to go down. Okay, therefore this is another 1 nanosecond to go down this one. I hope you can understand this one. Okay, so therefore this is how it will going down. Something like this. So the turn-off delay is very important, the minimum of the 2 and 3. For example, if at any case the wire A is changing from high impedance state, but it will take the value of the minimum value of the 2 and 1. Okay, the rise and fall, what is the minimum value is there, that value will be taken. Okay, so another way is that explicitly we can represent 3 delays. So something like this, 3, 4, 2. So now the rise delay will be 3, turn fall delay is 4, turn up delay will become 2. The same thing will be applicable to that one also. Okay, sometimes it is necessary to produce the delay values also. So according to the manufacturing point of view, we can mention the minimum delay, maximum delay, all these things as well. Okay, so the delays are either it is a rise delay, fall delay, all these things are separated by comma. Okay, for example, if you want to write minimum value, maximum values, you have to write, for example, you have to write A is to B is to C, something like this we need to write. Okay, in that perspective, I have written in this way. So this is also become, this entire thing is actually one type of delay only. One delay information only we have placed here. Okay, so what this one delay information? Okay, one delay information only we are giving. So that means 2, 3, 4. That is actually, first one is actually a minimum delay. Second one is a typical delay. Fourth one is a maximum delay.
Max.
Okay, so all these things will representing only one type of delay only. Okay, okay. Therefore, now only one delay information we have given. One delay means 3 different type of delays are there. So that means rise delay, fall delay,
Fall.
delay. So for that one, the max minimum value for rise, minimum value for the typical value for this thing, as well as maximum value for rise. All these things can be represented here. Okay, minimum value, typical values for the rise as well as the fall also. Okay, turn off is actually the minimum value of these things. Okay, it will take the minimum value. So therefore, whenever we are simulating something with this command, we can take the, whether you want to take the minimum values, whether we want to take the maximum values, or we need to take the typical values. Okay, so here it is possible to represent the 2 delays, something like this also. Okay, here the rise delay information, maximum, typical, minimum, as well as the fall, minimum, typical, maximum also possible. Okay, in this situation, turn off delay will becomes the minimum of these three things. Okay, let us incorporate 3 delays as well, 3 delay information as well. For example, something like this. For example, 2, 3, 4. Okay, so this is the raise information, maximum, typical, the minimum, typical, maximum. For example, 3, 5, 6 also can be taken. Okay, next 1, 2, 4, for example, something like this. Of A I am writing. So what it says that, the first information related to the rise.
Rise time.
The second information related
Fall.
to fall. The third one related to the
Turn on.
turn off. Okay, TT, turn off. TT. Okay, so that's how we can do. So the first one is always mentioning that minimum value, minimum value, minimum value. For example, if you write verilog, it's depending upon the type of simulator that you are using. For example, verilog, some delay ankondi, delay dot v. I'm going to consider the minimum values, min delays, which means that it will take only the values of the wire is something like this. The values of the wire ఏమవుతున్నప్పుడు మనకి wire can be something like this 2 comma 3 comma.
2, 3, 1.
So that's how it will take. Okay, for example, if you're writing the verilog delay underscore v plus typical. Okay, delay. So that's this keyword is depending upon what type of simulator that you're using. Okay, for the sake of simplicity, I'm telling you like that. Okay, wire typical delay means 3 comma 5 comma.
3, 5.
So like this, maximum value is also in the similar way. So far so good, everything's fine. Okay, now let us consider the delays related to delays gates. Fine. So let us talk about the delays related to the nets. Similar concept is applicable for the gates as well. Okay, but with the help of diagrams, then we can understand. Okay, for example, we take, this is the one AND gate. Okay, suppose this is A, this is B, this is Y. Okay, now it takes a delay of 2 timing units. It takes a delay of 2 timing units. Okay, now what is the way that I can write? For example, so what is the syntax? How can syntax can be written? And I can write.
And Y.
Okay, and here I'm going to write #2, and I can start off using values y comma a comma b. So as I mentioned that the name of the gate G1 G2 we have written, right? So that is optional. So without reducing the complexity, I'm not using that G1 G2 G3. If at all, if you want to write, you can write it here. G1 you can write it here. Okay. So but because of simplicity, I'm not going to write here. Okay, so what it says that this is how we can introduce a gate delay for an AND gate. Okay, so that means that the output y, what do you mean by this one? Output y will take this delay. So that's what the first important point that you should remember. Okay, the second point is that since we have given only one delay, right? So therefore the rise delay, fall delay, turn off delay, both are equal to 2 timing units only. Okay, whether it is nanoseconds or picoseconds and milliseconds, seconds, that is decided by the time scale directive. Okay, I'm not mentioning the time scale directive right now. That's the reason why I'm calling as 2 timing units. Right? Fine. So these are the 2 important points you should remember. Now let us consider one example. Okay. So for example, a timing waveform is something like this. Okay. Timing units is something like this. The signal, so something like this. So we have started off using this is 0 nanoseconds of time. For example, 0 timing units, 5 timing units, 10 timing units. I think I want to take a bigger one. Okay, so this is the thing. I'm considering that this is 0, this is the 5, 10 timing units, 15 timing units, 20, 25. Okay, now let us consider this is A, signal A. Signal B is something like this. Okay, signal B is something like this. Okay, B is this. Now A and B I have given. I want to define Y. I want to define Y. So how do I define Y here? That's the question. Okay. So now I want to define Y. Okay. So I need to mention that this is an AND gate having signal is A, B, Y. Its delay is equal to 2 timing units. Okay. 2 timing units I am considering. Okay. So let us start here now. So we have been starting from 0 nanoseconds that we are talking about. So at 0 nanosecond, please listen very carefully. So when A is equal to 0 and B is equal to 0 at 0 nanoseconds of time or 0 timing units, what should be the output signal for an AND gate? 0.
0.
So at 0 nanoseconds time, it should be there, right? But at 0 nanoseconds, 0 value cannot come at 0 timing units. Why? Because it takes some amount of the time. What is the time? Actually, this is a 0 is actually low value. That means that it is a fall delay. We can consider that. Okay. That means it takes some amount of the time. Then only it will produce an output signal, right? So therefore, up to 2 nanoseconds of time, we don't know what is the value. Okay. So therefore, we don't know anything about it, whether it is 0 or 1 and 0. Okay. So that means, for example, this is what 2 nanoseconds of time. Okay. It is, I'm writing here is 2 nanoseconds. 2 timing units. Up to the 2 timing units, we don't know. At 2 nanoseconds of time, yes, it is possible to know that there is a 0 value. Therefore, 0 value available at this point. Is it clear? Fine. Now, at this point, that 0, 0 will be assigned, the result value is equal to 0, we got that one. Now, this value will be available as long as there is no change at the inputs up to this point. So, at this point only, we can observe that at this point only, so at this point, I want to take another color, that's the reason why I'm searching. Okay, so at this point, there is a change is observed, right? So what is the AND gate output for this one? What is the AND gate output for this one?
1.
1 will be the output. 1 means, what do you mean by the 1? 1 means high value.
Rise time.
High value means rise. So it takes the rise time. Okay. So therefore, it cannot available as 1, but it has to wait for 2 nanoseconds. 5 plus 2 means what? 7. Up to 7 nanoseconds, the value will be 0. Then only it will start off using the logic 1. Okay. Then only the value will be logic 1. Clear? So that means that up to this point, what is happening here? Up to this point, 2 nanoseconds of delay it is waiting. So it is taking the 2 nanoseconds of time. Okay, then only it is raising. Okay. Now what is the next one? So it is keep on going to the high value. Okay, but here at 10 nanoseconds, you can see there is a change, right? You can see there is a change here. At this change, A is equal to 1, but B is equal to 0. That means output has to go to 0. That means 0 means what? Low value. Low value means T fall. So it take for fall also, since only one delay we have taken means fall also will be 2. So therefore it has to wait for 2 nanoseconds. That means up to 12 nanoseconds. 12 it will be there. Okay, then it is going down to 0. So therefore, what is happening here now? So there is some elapsement, there is some delay is elapsed here. This delay is actually 2 and going back down to 0, right? So again, what is happening here? So it is going down to 0 and 0 and 0 up to there is no change, up to there is no change. So but here again you find that there is a problem. So here also you can see there is a change. So what is the value of this one is? That is 0, right? 0 means it has to wait for another 2 nanoseconds to go, but actually the previous value is equal to 0, therefore it will be continuous. Okay, so therefore it will be continuous. So something like this, I'm using this black color. So this continues to up to this point. Okay, again, therefore you can see there is a change here.
1.
So it is a raise. So for this zero, it follows the same thing. Okay, it follows the same thing. 2 nanoseconds means it will wait for almost what is the value? 2 means 17. Okay, so but still we didn't find any kind of change. Therefore, it is going keep on going, and at 20 nanoseconds there is a find a change in A and B. Therefore, again it will go back to 1. So the 1 means it will go back to 1. 1 means it has to wait, of course, it has to wait another 2 nanoseconds.
22.
22. So at 22, it start off raising. It start off rising and come back to 1. Okay. So what is the delay that is elapsed here now? So the delay is nothing but again, I think it is better to take the color of magenta color only. Okay, so therefore it is taking that 2 timing units of delay rise. Is it clear to all of you? So what we expect the expected output is something like this. So the expected output is something like this. So this is what we are expecting. This is 0, this is 1, up to this is 1, go back 0, something like this. No, this is also 0, something like this. Right? This is what actually we're expecting. Okay, this is expected output. But real output is this one. But this is the real one is, this is the real one. Okay, is it clear? So therefore, since the gate is actually not a 100% accurate gate, therefore it has got some kind of delay. Therefore, the delay is modeled by using the delay information. Right? So this is how we need to look at the delay of the gate. Okay, fine. So shall we go for some more, one more example so that you can understand very clearly. Okay. For example, you take another example. Example 2. For example, one AND gate is here. One OR gate is here in this way. Okay, so it takes 5 timing units. It takes 5 timing units. It takes, for example, 4 timing units. Then what is the output value? So I am giving here is the inputs are A, B, C. My output is Y, for example. So here also without giving any kind of information, without complexity, I'm going to use only single delay, not 2 delays. Okay, 1 delay I'm giving. So 5 means rise delay, fall delay, turn off delay. So 4 means rise delay, fall delay, turn off delay of the OR gate output. Okay, fine. See here, so by the by, before going to that exam, I want to tell you another point here. For example, this is the text bench that we are giving. Okay, this is the information that you are giving to the uh, simulation tool. Then what is the test? How do we write a test bench for this waveform? How do we write a test bench for this waveform? So here I'm writing. Please understand. So I'm not going to write entire test bench. For example, I'm going to use initial statement, initial and end. So between that one only, this information I want to write it here. See, the input A and B is not uniform input. Okay, so we cannot find any uniformity in this waveform. So in that situation, I'm not able to write intelligently by using the for loop or by using the repeat loop on other things. Okay, so in that situation, what I can do directly, whatever the information is available here, that I'm using that one. Okay, how do we do this one? Let us start here. For example, A I'm writing, right? So A is equal to 0 initially and B is equal to 0. Okay, so therefore this is the first one I'm writing about. A and B at 0 nanoseconds of time I'm writing. Okay, so the change can be observed at 5 nanoseconds, right? The 5 nanoseconds that change is observed. So therefore I can write here is 5 nanoseconds. What about A here then? A becomes 1, B becomes 1, right? Now, there is a change is observed again at 10 nanoseconds of B only. A is same. So what is the suitable statement? Another 5 nanoseconds means 10 nanoseconds only. Okay. So after begin, I need to write initial and I need to write begin here. I forgot to write. If I write begin only, then only these things are added. Otherwise, it's not possible. Now, what about A, B, A here? A is not changing. Therefore, I don't want to write. Only B I want to write. That's all. Next, another one is another 5 nanoseconds. That means 15. At 15 nanoseconds, what I can observe? A is 0, B is equal to 1. Therefore, both I need to write. A is equal to 0, B is equal to 1. Okay. So next, another 5 nanoseconds. Another 5 nanosecond. That means 20 at 20 nanoseconds. That means that A will be remains no, A will be changes, but B is not changing. Okay, let it be like that only. But another 5 nanoseconds at 25, A is not changing. Sorry, yeah, both are not changing, right? So I want to keep it like that only. So whatever it may be. Okay. So that means simulation will stop at 30 nanoseconds means up to 25, A becomes 1, B becomes 1. Okay, so this is how we need to write a Verilog program, the test bench information when the waveform is something like this, right? So fine, only for the sake of information I have given. Now I'm going to give you another waveform here for this A, B, C. So accordingly, can you please write the what is the real output that we'll get? For example, A is equal to 10, 0. So 0, and this is at 5 nanoseconds or 5 timing units. And it will raise up to 1 at 10 nanoseconds or maybe 10 timing units. 15, 20, 25. Something like this. Therefore, this is the 15, 20. Okay, this is for example A. This is for example A. So B is something like this. Again, it is waiting for up to 10 nanoseconds. Available up to 20. Go back to 0. Now C is started off same value. Also high. C also, for example, the same as that of B, for example. So this is the B, this is C. Can you give me the output value, output waveform by giving this kind of timing units? So let us consider, this is called some X. This is called some X, that is intermediate line. Okay. So the moment A and B is connected to the AND gate, which is having the 5 timing units delay, that means that X, for X signal that is generated from A and B, will take a rise value 5, fall value 5, turn off value 5. Right? Similarly, for an OR gate, Y signal will take 4 units of delay for rise, fall, as well as turn off delay between X and C. Okay. So let us write now. How do we define this one? So first I want to consider A and B and I want to generate X signal. Okay. So let us write an X signal. X I want to write. What is the next signal? X is nothing but end of A comma B. So end of A comma B. Okay. So that is called X. So we started off 0 nanoseconds of time. So for the time being C, we don't want to consider the C, only A and B. So at 0 nanoseconds at a time, what we can observe? 0 value, but 0 value is not directly assigned as an output, but it has to wait up to 5 nanoseconds. That means up to 5 nanoseconds. What is the value of this one? It is unknown. It is unknown. So at 5 nanoseconds, the 0 will be assigned. Okay. Now this 0 will be available as long as there is no change in A and B. So this is observed that up to 10 nanoseconds, we don't find any kind of change. But at 5 nanoseconds, you can see here, at 5 nanoseconds, A is equal to 1, B is equal to 1. For an AND gate, what is the value? It becomes high. High ante it cannot give you directly the output. It cannot instantaneous output cannot be produced, but it takes some amount of 5 nanoseconds. What is the 5 nanoseconds of this
15.
one? 15. So at 15, it will go back to high. Okay. So therefore, what we can say that up to this point, how much time it waited? 5 timing units. Then it will go back to 1. Okay. So this is valid up to next change to occur. Okay. So up to this point, there is no change. That's the reason why the same output we observed there. But at the 20 nanoseconds of time or 20 timing units, you can find that there is a change in B. Therefore, what is the value that we can observe?
0.
Yeah, that is 0. Just wait. Yeah, that is 0. So for 0 is instantaneous value. Can we get? No.
No,
Because
25.
delay is involved in this one. So it has to wait another 5 nanoseconds.
5 times.
So another 5 nanoseconds means 25. Okay. So therefore, then 25 go down to 0. So therefore, again here what we observe that there is a delay is elapsed here. Okay. So this delay is actually fall delay. This is the 5 nanoseconds of time it will take. Clear? Now, so therefore it will go back to 0. If the signal is there, it will be 0. Otherwise, it will stop there itself. Okay. Next, what about Y? Okay. So let us write Y.
So why we should consider the delay one X or original X?
What does it mean?
We have to for Y we have to take the output X and C. Sir. For X we have to take delayed X or exact X.
No, X delayed version only we need to consider. X is whatever the X value that we got, that value only we need to consider. Okay, the X is generated based, the X is now this value. So initially we don't have any X value. Okay, this is the value is original value. Okay, so the original value is compared with C. Now what is happening here? See, observe. So here, this is 0, but this is unknown. For exclusive OR gate, for an OR gate, one is 0, another one is don't care means what? As all of you know that OR gate ki 1 వచ్చిందనుకోండి 1 వస్తుంది output. For example, OR if it is 0, it depends upon what about the signal. Okay, that means that whatever the signal is there, that value will be assigned here. So therefore, in that situation, X will be the signal for this. Okay, so therefore, it is also an unknown value. So up to this point, this value unknown only. Okay, up to this point, this value is unknown only. So now at this point, what we can see, the 0 is available. Is this 0 is instantaneously available to Y? No, it takes a moment of the time. That means this value is continuous. This value is continuous up to another 4 nanoseconds. What is the 4 nanoseconds that we have to give? Is it right? 4 nanoseconds. What is the 4 nanoseconds? I think it's 9, right? Up to 9.
9.
X5, this is 9. At 9, this value becomes 0, right? I think it is Yukarada. This is 9, for example. Okay, this is 9. Now at 9, yeah, we find that there is a 0 value is there. Okay, fine. Now 0 value is assigned here. Now, what is happening here? You can find at 10 nanoseconds up to until that means for another 1 nanoseconds, it will be the same. Another 1 nanosecond, that means 10 nanosecond. At 10 nanoseconds, what we can observe, there is a change
1.
between these two. Okay. So what is the value for the OR? This is the 1, this is 0. 1 0 means 1.
1.
So, but 1 cannot be instantaneous.
14.
It has to wait for 4 nanoseconds. What is this one?
Up to 14.
14 nanoseconds. So at 14 nanoseconds, it has to rise. Okay, so therefore, here what we can say that it has to wait for, it has waited for 4 timing units. So again, it is started fusing. So at this point, it is going and going, but here you can see that there is a change here. Okay, so there is a change here, you can observe. So what is the value? What is the value between these two? 1. So it will
1.
remain there 1 up to
Continue.
next change. Next change you can observe here only. Okay, so therefore here only you can see the next change, right? Here only you can see the next change. So therefore here C is changing, but X is not changing. But even though there is a change in C, therefore automatically it's computed. What is the value for that one? 0. Not 0, it's 1, I think so, right?
1.
1 only. So it is again, it will be 1 only. It will go something like this. But now here you can see.
24.
So this is up to at what value?
24.
25. No, 25 no.
24. 24.
Why it is 24?
1 plus 1, 1. After 1, we'll get up plus 4. No, sir. Up to 24, we'll get.
No, not like that. So, yeah, exactly. So at this point, 20 nanoseconds is there. It is waiting for 24 nanoseconds, right? Exactly, 24. So at 24, what is happening here? It has go back down to 0. So at 24, wait cheyagada 5 work wait chestunnadi. Okay, so it has to go down. Okay. So you can find changes here up to this point, okay? And at here, what is happening here? Again, it has to assign the value to another 4 timing units. Okay, it go back to the 5 timing units, but there is no change here again. Of course, up to this point, it will be there. At 25 only, it will be available. Okay, because yes, of course, it will be 24, but there is no change at the 24 also, right? So again, it will be continuous. Okay, now at 25, you can find a change here. So that means another 4 nanoseconds it will take. So it will take another 4 nanoseconds. That means 29.
At 29,
it will be 0. Right. So therefore, here is it is actually taking 24 times 4 nanoseconds time. It is visible at 4 nanoseconds very clearly. Okay. So this is how we have to think about the delays when the delay is modeled in any circuit. Is it clear? So this is all about the delay information, and we have completed the delay information with this. and we can see the remaining things. That means strengths information is there. We will see the strength information in the next class. Okay, so if you have any doubt, you can ask me. Otherwise, we can stop it here. Okay, we don't have any doubt, then we will see in the next class. Thank you.